Hi everyone. In this video we're going to discuss how to compute the length of a curve given by parametric equations. So suppose in the plane we have our favorite curve, and here's where it starts, and maybe it loops and it finishes here. Yeah? In this curve, let's call it C, has coordinates given by the functions x of t, comma y of t. And the discussion that we'll have with regard to this beautiful curve is in R2, but the ideas will naturally extrapolate to higher dimensional spaces as well. And suppose that this coordinate is C, the curve, the coordinate here, evaluated at some time A, and this point here is the curve evaluated at some time B. And the time's going to range between those values A and B. Let's further stipulate that x prime, so the derivative of x and the derivative of y, are both continuous functions. How can we find the length of this curve? Let's find the arc length. And usually we denote this S for arc length. To do this, what we're going to do, it's very calculus-y, right? How do we compute the length of this curve? We're going to break it up into smaller line segments. So we're going to approximate this curve by line segments. And we're going to compute the lengths of the individual lines and then add them all up. And then, of course, we're going to take a limit as the number of these line segments goes towards infinity. So our line segments will look something like this, right? And we can see, hopefully, it's intuitively clear now that we know a lot of calculus, that this does, in fact, approximate, maybe not well, but it approximates the length of this curve nonetheless. And as I add more and more points, the approximation becomes better and better. So how do we formalize this? Well, of course, because we're in calculus, we need a partition. So we need to partition the interval of time from A to B. And we're going to do it in the following. We're going to let A be called T naught, T0, and, T1, all the way until we have T sub n, which is our last point B. And so here is C at the curve, the coordinate of the curve at T0. This next point is, say, C at T1. This one is C at T2, and so on around the curve. Yeah. What is the length of the curve? The length of the line segment just on the interval from T sub I minus 1 up to T sub I. What's the length of the curve? Well, let's look at the length of the line segment, rather, from C of T1 to C of T2. That's a straight line. How do we compute the length of that? And remember that we know the x and y coordinate at both of those points. How do we find, really, the distance between these two coordinates? We need the distance formula, or the Pythagorean theorem, however you want to think about it, right? So the length on this interval will be approximated by the length of the line segment, which is just the distance formula. It's going to be x at ti minus x at ti minus 1, quantity squared. Scroll up a little. Plus y of ti minus y of ti minus 1, quantity squared. Yeah? And this is the length of the line segment, and we know that this does approximate the length of the curve on this interval as well. Now we want to use a little bit of calculus. As we recall, x of ti, or of t sub I, minus x of t sub I minus 1. This quantity hopefully looks familiar with our knowledge of the mean value theorem. And remember, our assumption here is that x prime is continuous, so the function is certainly differentiable, right? So we have the mean value theorem. Let's use it. By the mean value theorem that you learned in Calculus 1, there exists, and I'll start using the symbol with the backwards e, there exists some value t sub I star in between t sub I minus 1 and t sub I, such that the difference, x of t sub I minus x of t sub I minus 1, is equal to the derivative of x at some value, some test point, ti star, times ti minus 1. Yeah? So the difference in the function values is equal to the derivative, the value of the derivative at some point times the width of the interval. And this is the mean value theorem. And instead of ti minus 1, we're going to write this as delta t sub I. So we have x ti star times delta t sub I. And we're going to do this again for the y's. Again, by the mean value theorem, we know that there is t sub I, let's give it 2 stars. It's a different point. It's not the same test point as we had up here. Maybe it's different. Who knows? But the intervals are going to be so small that it really won't matter in the end once we take a limit. So we know that there exists a point t sub I double star in the same interval, ti minus 1 comma t sub I, such that y of t sub I minus y of t sub I minus 1 is equal to y prime at t sub I double star times delta t sub I. Yeah? And I hope that this is familiar. I hope that we've seen these ideas whenever we took single variable calculus. So how do we compute the total length? How do we compute the total length? The arc length S is going to be approximated by the sum of all of these quantities, right? So we know that if we take a limit as n goes to infinity, and if we add up all the arc lengths of all the tiny little line segments, of these lengths, so we know that S is going to be the sum of all the lengths of all the line segments. What do we know about now by our mean value theorem computations? The change in x, this guy, is going to be the derivative at a point times the change in time. Similarly, the change in y is going to be the derivative of y, here it is, at some point times the change in time. So let's plug that in. We have the arc length is equal to the limit as n approaches infinity times the summation. And now we have x prime of ti star squared plus y prime at ti double star squared. And whenever we pull out, whenever we square the delta t, each one of these will have a delta t squared. I can pull it outside the square root and just have a single delta t sub I. And because delta t sub I is positive, the absolute value doesn't matter. So it's just still delta t sub I. And I hope that this looks familiar now. This is a nice little Riemann sum, right? And now as the number of line segments goes to infinity, the length of each of the line segments goes to 0. Each of these test points becomes essentially the same thing, and we are left with the integral from a to b of the square root of dx dt squared plus dy dt squared. And then my delta t becomes a dt. Yeah? Perfect. Let's do a quick example. I know what you're thinking. Boy, gee, howdy, I already know how to compute arc length, right? We hopefully have seen an arc length equation already. But now we have it with parametric equations. So let's make sure that they are consistent. Let's let y be the function f of x. And I want to find the arc length of this function f of x, right? So let's find the length of f of x on the interval from a to b. Well, first we need a parametrization. What's a parametrization that we can always use on a function y equals f of x? It's our easiest parametrization that we have. Right. The standard parametrization is x equals to t and y equals to f of t. And t will now vary from a to b. Yeah? And now we can plug this into our arc length equation. We know that s is equal to the integral from a to b square root of dx dt squared plus dy dt squared dt. Plugging it in, integral from a to b. What's dx dt? Well, it's the derivative of this function with respect to time, which is 1 plus, what's dy dt? That's just the derivative of f, right? And what's the derivative of f? It's just f prime. And I hope that this looks familiar to something that we've already seen. All right. And there will be more arc length equations, but we know that if you have to compute the length of a curve, it boils down to a nice fun integral with square roots. And keep in mind that this is the Pythagorean theorem. Well, it emerges from the Pythagorean theorem, right? And so often you will see some trigonometric substitution in these problems, so be sure to keep your techniques of integration fresh whenever you think about these problems. All right, let's think about something slightly different. Let's think about area. Let's suppose we have our favorite function. Yeah? Here is y equals f of x. And in this case, what do I have about my favorite function? This function is positive. Yeah? And suppose that I want to find the area of the region. Bounded between the curve y equals f of x and the x-axis. Between x equals a and x equals b. And this is a terrifically easy question, isn't it, right? This is like day 3 of Calculus 2 whenever you learned how to do integral things. We know that this area is equal to the integral from a to b of f of x dx. Dx. Let's see another way that we can compute this integral. I know that f of x is really y, isn't it? I know that this is really the integral from a to b of y dx, and things are starting to look a little funny now. Suppose we actually have a parametrization of this curve, given by x is some function of time, and y is some function of time, y of t. And t now varies between some number alpha and some number beta. So specifically, what does this mean? X of alpha is equal to A, and X at beta is equal to B. Well, let's plug it in. It's going to be the integral now from alpha to beta for time. We're going to change everything to time. Y is now y of t. Dx is now x prime of t dt. And this allows us to compute area underneath curves, positive curves, whenever we have a parametrization of that curve. And this is super nice for some functions because computing the integral of this type of thing might be hard or terrible, but if we have a parametrization, it might simplify it. And let's see an example of when that occurs. Indeed, we have an ellipse. Let's consider an ellipse. Find the area. Of the ellipse with equation. X squared divided by a squared plus y squared divided by b squared equals 1. Okay. For this problem, I want you to think about it first. So we now know how to compute the area with the parametrization. We know how to parameterize this curve. Pause the video, try to figure this problem out yourself. All right, so we know that a parametrization is going to be x equals a cosine theta, y equals to b times the sine of theta, and theta will range between 0 and 2 pi. Yeah? So let's see how to use this. I know that this parameterizes the entire circle, or the entire ellipse, rather. Let's draw the ellipse. Suppose here's A, here's B, and it looks something like this, a little football. To use the formula that we derived, we need a positive function, right? So we need to really limit our theta and find the values of theta so that we go from negative A to A and traverse all of this positive piece of function, and then multiply it by 2. Does that make sense? So really what we want to do is do twice the integral What's the value of theta that gives us the left part of our football? It's pi. And the value of theta that gives you the right part of your football is 0. And now it's going to be b times the sine of theta. There's your y. And dx is now negative a times the sine of theta, d theta. And if you haven't done so, pause the video, be sure that you're okay with this integration. All right, so let's make sure that we're okay. This will be equal to, my minus sign will flip the bounds of integration. So we have 2b, or 2a times b, integral from 0 to pi, sine squared theta d theta. We know that we need a trigonometric identity here. This becomes 2ab, integral from 0 to pi, of 1/2 minus 1/2 cosine of 2 theta, d theta. Oops. Integrating now gives 2ab times 1/2 theta minus 1/4 sine of 2 theta. And we want to evaluate this from 0 to pi. Luckily here I know that sine of 2 pi is 0. I know that sine of 0 is 0. So all that I really am left with is 2ab times 1/2 pi which is pi AB, which is the area of an ellipse. So this is super cool. If you didn't know the area of an ellipse, here it is. What do we know about an ellipse where the major and minor axes are equal? Maybe they're r, right? Suppose A and B are both r. What's the area? You get pi times r, which is pi r squared. And if A and B are both r, that is indeed a circle with radius r. So that's kind of nice that it's consistent. All right, everybody, I hope that this helps. If you have any questions about the content in this video, please don't hesitate to reach out and ask. Thanks so much, and I'll see you in the next video.